So we are talking about the properties of the system. Okay, so for the properties of the system, you already know that there will be some properties that we define as the pressure, volume, temperature, mass. Okay, so in order to define our thermodynamic system, we deal with some these type of properties. Okay, viscosity, electrical resistance, thermal conductivity. Then there will be a type of properties. First, we call as a intensive properties. Intensive properties which is independent of the mass of the system. For example, your velocity, elevation, height. Okay, so these are independent of your mass of the system. So these are the intensive property, and then there will be extensive properties which are dependent on your system mass. That is the pressure, and then there will be a density, and any other property that is dependent on the mass is the extensive property. Then some of the properties you can come across in this course is the specific properties. The specific property, for example, your enthalpy, your specific volume. So these are also the type extensive properties per unit mass. Okay, so these are the three different properties which you can come across in any of your thermodynamic system. Okay, so you know how these are characterized and what is the meaning of these properties. Then you already know that whenever we are talking about thermodynamic system, so you have a state, and the state is that the set of property to completely describe the condition of the system is known as the state. For example, if you start your car engine, okay, so initially it is cool, then with the time it will start heating. So it is the combination of different states. Okay, it cannot be like this that you just start your car and it immediately achieve the temperature of 400 degrees C or something like this. So it will have to follow some states, follow some points in order to get to that value. So these points are called the states. Okay, so that will also explain from this thing that initially your state is, for example, mass is 2 kg, temperature is 25 degrees C, and volume is 1 meter cube. But with time, it will be that as your piston move, as the compression and expansion started, okay, it will be changed to state 2, and that will be your state 2. Okay, so whenever we are talking about this thermodynamic system, it will definitely have to go from state 1 to different state. If it cannot go from state 1 to another state, it means that your thermodynamic system is not started yet. Okay, because it will already on the state 1. Okay, and whenever we are talking about thermodynamic system, there will be a term equilibrium that is called as a state of balance. Okay, the state of balance means that there will be a thermal equilibrium. Okay, the thermal equilibrium have to define that there will be no temperature gradient throughout the system. Okay, then there will be a mechanical equilibrium, that no pressure gradient throughout the system. Then phase equilibrium, system have more than one phases and mass of each phase is in equilibrium. Okay, chemical equilibrium, chemical composition is constant and no reaction occur. So I hope you already have the knowledge of these things, because I am not going in the detail. So I'm just going through the quickly so that you have to know that what we have to do in this course. Okay, so then there will be a call as a process. Any change in the system undergo from one equilibrium state to another is known as process. Okay, for example, if the system go from state 1 to state 2, it has to follow some process. Okay, so and the series of states from which the system go is called a path. Okay, so any path that followed by the system to go from state 1 to state 2 or any other state, it is called as a path. And this is your example. For example, the system goes from state 1 to state 2, so it have to follow some path, and that path is represented by the solid line. Okay, then there will be a term as a quasi-equilibrium process. Quasi-equilibrium process is basically a process proceed in such a manner that system remain infinite infinitely close to. Okay, there will be a term that this is called this will be a confusing, this is called remains a very smaller time. Okay, for example, uh, if a system for example there will be a mass there will be a piston cylinder arrangement, for example, and if it goes from state 1, for example, this is your state 1 and this is your state 2, okay, and from going from state 1 to state 2, if it takes some time and but the change in the system properties, for example, the change in pressure, temperature, volume is too small, so then we can define it as a quasi equilibrium process, but that is only happen for a very small time, okay, so that term is called a quasi static or quasi equilibrium process, okay. So if you have to understand well, you have to go through your book also, okay, so you can get the knowledge, because I'm not going in detail, because this is a complete one lecture on these things, that what is the quasi equilibrium process and what is these things. Okay, so next thing is that the process path is continuous line only if it is having a quasi-static process. This is the important thing, that whenever there is a quasi-static process, that it is a combination of small states, okay, which have us. If it is a quasi-static process, then we can define it as a solid line. But if it is not a quasi-static process, then it is denoted by the dash line. Okay, so you can come across the different problem that these are the quasi-static process. So you have to know that how you build your PV diagrams and TS diagram. Okay, one thing you want to give me some information, that you already know that how to build the PV and TS diagram. Anyone can confirm?
Yes, sir. We have studied about
Yes, sir.
PV diagrams and
Okay.
TS diagrams, and
Okay.
but we have not studied about this dash line concept, non-quasi-static process.
Okay. Okay, I will give you the lecture on this also. When we try to solve the problems, then I will just give you the brief about that how you can build these dash lines and these one. Okay.
Okay, sir.
Okay, then there will be a terms as the isochoric process and isobaric processes. These are the processes, for example, isochoric process. Isochoric process in which your volume is constant, okay. So this is your PV diagram, okay. Whenever we define there will be a volume is constant, isochoric process. When we can define there will be a pressure is constant, it is defined as a isobaric process, okay. So P is constant, isobaric, and then if the enthalpy is constant or entropy is constant, it is called as a isoenthalpic process and isoentropic process, okay. So then there will be, if the temperature is constant, it is called the isothermal process. So these terms you can, I think, many times use in your thermodynamics 2 course as well. So you all have the good knowledge that what is these isochoric processes and isobaric processes, okay. Then there will be a term as a cycle, okay. Cycle for any thermodynamic system, it if it has the state 1 and if it has a state 2 and if it come from state 1 to state 2, then it is called a cycle. So anything that complete the one cycle is called the, we can define it as a cycle, okay. So and cycle, the term cycle, basically we define a thermodynamics. So for example, your turbine, okay. So whenever you have to go from state 1, okay, then you have to go to state 2, okay. So this is your cycle. Okay, then you already know that what is the reversible processes. Reversible process that can be reversed without leaving any trace on the surrounding. Okay, that come. Yes, anything? Student, please mute your sounds. Mute your. Kindly mute your microphones. Okay. Reversible process that can be reversed without leaving any trace on the surrounding, okay. So any process that can come from state 1 to state 2 we can call as a reversible process, but it is an ideal process. It cannot be happen in your daily life that there will be a reversible process. Most of the processes are irreversible, okay. So both system and surrounding are returned to their initial state at the end of the process. That is called as a reversible process, and this is only possible when net heat and net work exchange and between the system and surrounding is zero for the process, okay. So there will be a concrete, for example, this is your pendulum However, we idealize that the pendulum system is a reversible process. However, there will be some loss of energy and it cannot come to its initial stage without losing some of the energy. But ideally, we call it as a reversible process. Okay, so the same terms, the quasi-static process is also a reversible process. Okay, and then there will be a reversible process, and most of them haven't taken place and they cannot reverse themselves spontaneously and restore the system to its original state. For example, there will be a cup of coffee and you want, and its temperature, initially its temperature is 100 degrees C and you have to cold it. Okay, so it can go from the surround, it can achieve the surrounding temperature. Okay, but it cannot go back from the surrounding temperature to again 100 degrees C without having work done on it. Okay, so this is how the irreversibility you can define it as. So you definitely, if you want to make the coffee hot again, you want to do some work and you maybe you want to heat it. Okay, then you can achieve that same temperature which is at the state 1. Okay, so this is your irreversible process. Okay, so this again, this is one is that the hot cup of the coffee cool down. Yes, yes, please.
सर जब चाय गर्म होती है सर, हम उसके ऊपर हलाते हैं सर स्पून के साथ, हम उसके बाद वर्क डन कर रहे होते हैं एडिशनली सर, वो तब ज्यादा जल्दी ठंडी होती है, हालांकि हम उसके अंदर वर्क डन कर रहे हैं। ऐसे मेरे साथ जब वो नॉर्मल टेम्परेचर पे पड़ी रहे, हम उसको कुछ भी ना करें तो सर वो देर से ठंडी होती है। जब हम उसको हलाते हैं सर तो ज्यादा जल्दी ठंडी होती है, हम उसको वर्क डन भी कर रहे होते हैं। उसका क्या रीजन?
नहीं, उसमें तो ये है ना कि आप एक्सटर्नल, अब जो आप उसको कह रहे हो हिला रहे हैं, वो तो आपका कन्वेक्शन प्रोसेस हो गया कि आपने उसको एक जो है ना मीडियम दे रहे हो जिससे आप उसको ठंडा करना चाह रहे हो। लेकिन यहाँ पे हम इरिवर्सिबिलिटी की बात करें, फॉर एग्जांपल अब मैंने यहाँ पे उस चीज़ की कोई रिलेशन नहीं है जो आप बता रहे हो कि हमने उसमें स्पून हिलाया तो वो ठंडी हो गई। ठीक है, ये तो आपने एक एक्सटर्नल मीडियम दे दिया। फॉर एग्जांपल अगर मैं उसको फूंक मारना शुरू कर दूं तो वो भी ठंडी हो जाएगी। लेकिन वो यही है कि मैं कन्वेक्शन प्रोसेस में एक्स्ट्रा मीडियम दे रहा हूँ उसको कूल करने के लिए। लेकिन यहाँ पे बात ये हो रही है कि अगर कॉफी गर्म थी तो वो ठंडी तो हो जाएगी जो कि रूम टेम्परेचर के मुताबिक, लेकिन अगर हमने उसको दोबारा से गर्म करना है तो उसके लिए हमें एक्स्ट्रा वर्क की जरूरत है। तो मतलब ये है कि हम गर्म कॉफी से ठंडी तो कर सकते हैं, लेकिन ठंडी से अगर आपने उसको ऑटोमेटिकली गर्म करना है तो उसके लिए हमें वर्क डन की जरूरत है। और जब भी हमें वर्क डन जरूरत पड़ जाए किसी भी स्टेट 1 से स्टेट 2 पे अगर कोई चीज चली गई है और स्टेट 2 से स्टेट 1 पे लाने के लिए, तो दैट विल बी कॉल्ड एज अ इरिवर्सिबल प्रोसेस। ओके, सो दिस इज द टर्म डिफाइंड एज अ इरिवर्सिबिलिटी। Then why reversible process? Okay, why reversible process? Okay, most of the thermodynamic system which you are dealing in your thermodynamic course, we just idealize it and we just assume that these are the reversible process. Why we do that? Okay, because it is easy to analyze. Then system passes through series of equilibrium, and whenever there will be equilibrium states, then it will be the problem becomes so easy. Okay, then serve as idealized model for actual process to be compared for analysis and views as a theoretical limit for corresponding irreversible one. Okay, so that's why we mostly focus that we assume that the process is reversible process, okay, rather than irreversible process. Okay, because irreversible process is very difficult to analyze. Okay, then there will be a term as a temperature. Okay, so temperature, there will be no exact definition, only we can define as a degree of hotness or cold. Okay, or that is depend upon your psychological sensation also. Or for example, if you can just say that metallic chair may feel cold than the wooden chair, even it has the same temperature. Okay, so that will be defined as a temperature. You can just define because it will be a psychological sensation that you feel it. However, the temperature will be the same whether it will be a metallic or a wooden chair. Okay, so there will be no exact definition of temperature. Okay, only if we can just go for technically, it will be a change in temperature gradient. Okay, and then it will be called as a temperature. So then you already know that some of the temperature scales. Okay, so there will be a Celsius scale, Fahrenheit scale, Kelvin scale, Rankine scale. You all so have good knowledge about how to convert from one scale to another scale, because this thing we frequently use in this course, that if one state is given on Fahrenheit and you have to convert it into the Celsius scale, so you also know that how to convert it. Okay, So these are some basic definition. You have to go through it by your own. Okay, then okay, the main thing is that how to, okay, this is the conversion factor. So you already have the knowledge about that how to convert it. So you know that whenever you want to study this course, you have these terms on your fingertips. Okay, that how you convert from, for example, if you go for Kelvin, you have to convert from Celsius to Kelvin, you have to add 273.15. When you have to go from Fahrenheit to Rankine scale, okay, and another thing is Rankine scale and Kelvin scale is most commonly used in this course. Okay, so you have to know that what is the Rankine scale and the Kelvin scale. And then there is a Fahrenheit scale. Okay, so how to convert it, and then okay, pressure you also know that normal force exerted by fluid per unit area. Okay, and the unit of pressure are different one as we go from SI units, the Pascal, kilopascal, megapascal. You have to know that how to convert it from megapascal to kilopascal, how to convert from bar to Pascal. Okay, so these are some conversion factors. Okay, and you have to use these factor more frequently in your course as well. Okay, so these are some SI unit. I will pass this slide to you after this lecture, and then you have to go through it before we can start our next lecture that will be on the next days. Okay, then there will be English units, that is the pounds per square inches. Okay, so this is also some units that we have to see in this course. However, most of our examples are based on SI units. Okay, then there will be a term as a pressure. Okay, absolute pressure. Absolute pressure is the actual pressure at the given position. Okay, and it is measured relative to absolute vacuum. That is the absolute zero pressure. Okay, and then as you know that the pressure gauges which you commonly use in your houses and you commonly see in everywhere is designed to indicate zero at local atmospheric pressure. And whenever we talking about the gauge pressure is the difference of absolute pressure minus atmospheric pressure, and pressure less than local atmospheric pressure is known as vacuum pressure. Okay, so this is the vacuum pressure. If I just give you some sort of example or anything in the later lectures that has pressure given as in the absolute, and I want that you have to convert into the gauge pressure, so you have to know that how to convert into the pressures into different pressures. Okay, so these are some of the terms pressures one. Okay, so this is your different pressure, so you have to just go through it that how you convert from gauge to absolute and absolute to ATM pressure or something like this. Okay, then there will be a term as the ideal and real gas. Okay, so any equation that relate the pressure, temperature, specific volume of the substance is known as equation of state. Okay, so these are most commonly we use in the thermodynamics, the equation of state. Okay, which is P V is equal to C. Okay, and this is the one of the equation example of the equation. Okay, then you already know that there will be an equation which is called an ideal gas equation. Okay, so also you come across many times this equation that PV is equal to RT. So you have the knowledge about that what is the PV and is equal to RT, and they will be constant, and T is the temperature. Okay, so this is your ideal gas equation. Okay, so this is the hypothetical gas that obeys this law is known as ideal gas. Okay. So then there will be a thermal equilibrium. So you already know that each system try to attain the equilibrium. Okay, so there will be no change with respect to temperature, no temperature gradient. Okay, there will be again that if you just put the cold drink on your table, it will try to achieve the same temperature of the room temperature. So it means that any system you just thermodynamic system is trying to achieve the thermal equilibrium. Okay, so this is the some concept about thermal equilibrium. So heat and work. Okay, so anyone can confirm me that you already go through this type of that thermal equilibrium, mechanical equilibrium in your thermodynamics 1 course.
Yes, sir. We are familiar with all of this.
Okay, okay, good. Okay, so heat and work, this is also one of the familiar things that most commonly we see that there will be a two type of boundary system in two forms energies. Okay, that will be in terms of heat and work, or we come across these type of things many times in this course. And heat is a form of energy transfer between two systems, okay, by the temperature difference, and heat is the energy in the transition, okay. And so this is type of heat and work. Okay, so okay, then there will be a terms as a conduction, convection, and radiations. Okay, so convection, you also know that transfer of energy from one more energetic particles of the substance to adjacent less energetic one as a result of interaction between them. Okay, so conduction is more a physical process. Okay, so it will be a transfer of energy from one place to another. Okay, so this we can define as a conduction. In convection, when we are transfer of energy between a solid surface and there will be a fluid that is in motion. It involves both the combined effect of conduction and fluid motion. So whenever there will be involvement of fluid motion, for example, if there will be a cup of coffee and I am just throwing blow the air over there, okay, so then it will be a convection process. Okay, but if there will be some sort of iron bar and that was just placed over the table, okay, and I am blowing some air over there also, and there will be a heat transfer between that bar and table also, then there will be a conduction and convection process simultaneously also. Okay, so and then there will be a third term, that is the radiation. The radiation is defined as a transfer of energy due to emission of electromagnetic waves. Okay, so whenever there will be a emission of energy and any terms from electromagnetic wave, it is called as a radiation. Okay, so this is also the basic concept of conduction, convection, and radiations. Okay, so heat and work. You also know that work is energy transfer associated with the force acting through the distance. Okay, and it is defined as joule or kilojoules. Okay, so then there will be a specific work. Specific work is a type of work in which is defined as a work per unit mass. Okay, so this is the joule per kg. So this term is specified for the term that is the specific work. Power, work per unit time. Okay, so and okay, the most important thing is the conventions. Sign conventions. Most of the thermodynamic system when you are analyzing, so you have to use these frequently. That whenever we are I will call this as a heat transfer to a system, it can be considered as a positive one. Then heat transfer from a system, it will be a negative. Then work done by a system, it is positive, and work done on a system, it is negative. So these are the sign convention which we commonly use when we are analyzing our thermodynamic systems as well. Okay, so these are some of that. If Q is going out and Q is going in, and W is going out or W is going in. Okay, so you can go through this picture as well. Okay, then there will be a most term we define when we are defining our thermodynamic system. We use a term specific heat. Okay, so specific heat, how we define the specific heat? Different materials require different amount of energy for their temperature to increase through unit quantity, okay, for identical mass. What does this mean? This means that, for example, if I have 1 kilogram of iron and I have a 1 kilogram of water, okay, and I want to raise temperature of both from 20 to 30 degrees Celsius. So each of them require different type of energy to raise that 10 degrees C. For example, if 1 kg of iron need 4.5 kilojoule, however, if 1 kg of water need 41.8 kilojoule. So this term is defined as a specific heat. Okay, so this amount of energy which is required to increase the unit quantity for identical mass is called the specific heat. Okay, so hence it is required to define the property to compare the energy storage capacity of different substances. So this also term specific heat you come across many times in this course as well, and this property is known as specific heat. Okay, then there will be okay, this one, specific heat at constant pressure, CP. So CP and CV also you can commonly see in this course, the energy required to raise temperature of the unit mass of the substance by 1 degree as the pressure is maintained constant. Okay, if pressure is constant, then it is called as a specific heat at constant pressure. And then specific heat at constant volume, the energy required to raise the temperature of unit mass of the substance by 1 degree as the volume is maintained constant. Okay, so CV when there will be a volume is constant. Okay, so you have the better knowledge about CP and CV as well. Okay, and when we are talking about CP and CV, one thing which you have to memorize is that CP is always greater than CV. Okay, the reason is that as the system is allowed to expand in case of constant pressure, because CP is the constant pressure one, and energy for this expansion work is also needed to be supplied. So we have to supply some energy. Okay, whenever we are expanding in case of constant pressure. So that why CP is always greater than CV value. Okay. Okay, then you already know that how you define the enthalpy. Enthalpy is U plus PV. Okay, PV is equal to RT from come from ideal gas. Okay, so this is your basic, and this is your final relation, that is CP is equal to CV plus R. Okay, so this also, this relation you commonly use in your thermodynamics 2 course as well. Okay, so you have to better know about the units as well, kilojoule per kg dot Kelvin. Okay, then there will be a term as a work done. Okay, so whenever we are talking about work done from state 1 to state 2, okay, so we have to draw some of the PV diagrams. Okay, and you already know that area under this curve is work done. Okay, so this is how we define the work done. Work done from state 1 to state 2 is that is equal to this relation. Okay, so this is come from the area under the curve. Okay, so this is the most familiar work done equations. Okay, so this one. Okay, then there will be a first law of thermodynamics. First law of thermodynamics is also known as law of conservation of energy. Okay, so this is a very simple one, that energy can neither be created nor destroyed during the process, but it can only be transformed from one form to another. For example, if I throw the stone from some height to the ground, there will be a potential energy of 10 kilojoule, kinetic energy is 0. However, when that stone hit the ground, that potential energy is changes into the kinetic energy. So it is not destroying, it is changing from one state to another one. So this is the first law. This is how we can define the first law. Okay, so this is the basic equation of the first law. Okay, and then okay, the most commonly we use the first law equation is that energy in minus energy out is the equal to the change of total energy. Okay, so whenever we are analyzing our thermodynamic system, we have to develop some equation, and that equations are developed from the application of first law of thermodynamics. Okay, so I will just going through it, and I will give you a complete lecture when we are solving these problem, that how you can apply this equation for your thermodynamic system as well. Okay, so then there will be a second law of thermodynamics. Thermodynamics second law is energy is the ability to bring out change, about change or to do work. And second law of thermodynamics state that in all energy exchanges, if no energy enter or leave the system, the potential energy of the state will always be less than that of the initial state. Okay, so this is also commonly referred as entropy also. Okay, what is the significance of the second law of thermodynamics? So because the second law of thermodynamics is not just limited to identify the direction of the process, it also asserts that energy has the quantity as well as the quality. Okay, and mostly whenever we are talking about say a system like heat engine, refrigerator, it work on the second law of thermodynamics. Okay, and whenever we are dealing with the thermodynamic system, there will be two common things, that is the source and sink. Source is from where you are supplying your heat, and sink is where you are rejecting your heat. Okay, so these are some common things which you are used whenever you are analyzing your thermodynamic systems. Okay, and okay, second law of thermodynamics, heat engines. Okay, so this slide you can just go through by your own. Okay, there is nothing inside it. Okay, because okay, the characteristics of the heat engine. Okay, so heat engine, whenever we are talking about heat engine, we also know that they receive the heat from high temperature reservoir, that is called as a source, and that source come from any type of energy source, that can be a solar energy, that can be oil furnace, that can be a nuclear reactor, or that can be a battery or anything. Okay, so they convert part of this heat to work. Okay, and usually in the form of rotating shaft. So we are what we are doing, we are taking a work from the heat engine. So we are producing work, and that work is produced either by rotating the shaft, and then there will be a rejection of heat, and that rejection is from the sink. Okay, and that will be rejected to the atmosphere or any type of sink. Okay, and they operate in a cycle. Okay, so and heat engine are generally work for the producing devices. So these are type of the gas turbine, IC engine, steam power plants. So in this course, that is thermodynamics, we will study gas turbines, IC engine, steam power plants in the detail and how we analyze these type of systems. Okay, so this is how you can schematically draw your heat engine. Okay, so if you can see that heat engine, there will be a high temperature source, that is the Q in. Then there will be a W net, that is your work done, and then there will be a sink, and which is the your lower temperature Q out. Okay, so this is how you can just define your heat engines. Okay, the similar example for the steam power plant. In the steam power plant, the same type of things we are seeing, that there will be a supply of heat in the form of source, that is the boiler. Okay, then there will be a turbine. In the IC engines and in the engines, there will be a shaft. Okay, rotating shaft. Here there will be a turbine from where we can get the work out, and there will be a condenser which is called as a sink, and there will be a pump where we are inputting our power. Okay, so this is how you can commonly describe your thermodynamic system. So whenever we are when we start our thermodynamics 2 course, I will give you the explanation about how you build your PV and TV diagrams to analyze these type of system. So right now I'm just going through it, that how this system look like. Okay, so this is the without heat rejection. Okay, so this is the same thing. Okay, and okay, so next thing is that you also have the knowledge about the thermal efficiency. That thermal efficiency is defined as net work output over total heat input. Okay, so this is how you can define your thermodynamics system, thermal efficiency. Okay, so okay, and so this the slides which I'm just going through it, you have to go through by your own, because this is also a revision process. Okay, so because I'm not going to explain each and everything. Okay, then another important thing is a refrigerator and heat pump. Okay, so whenever we are talking about refrigeration process and heat pump, you see that there will be a condenser. Okay, the same thing like in the turbine one, and then the compressor. Okay, and previously the main difference between the refrigerator and your this one, okay, is that in this one there will be a turbine and there will be a pump. Here there will be a pump, and here there will be a turbine. However, in the refrigeration process, here there will be a compressor, and here is the expansion valve. So I will give you the explanation about that what is the purpose of this expansion valves and compressor. But right now you just have the knowledge about how your refrigerator system look like whenever we are drawing our thermodynamic system and whenever we are analyzing our thermodynamic system. So these are the four main component of our refrigerator and heat pumps: condenser, compressor, evaporator, and expansion valve. Okay, and then there will be a heat pump also, refrigerator and heat pump. Similarly, as we draw the schematic of the IC engine, internal combustion engine, we just have the develop a schematic of the refrigerator as well. Okay, in the same way. Okay, so this is it. So this is your thermodynamic revision. So I will pass this lecture to you, and in the next class, inshallah, we will go for the your thermodynamics 2 lecture, which we will start from uh, this one. This is your outline for the next lecture. So we will start from the vapor power cycle. Okay, so gas power cycle, chemical reactions, compressibles. So these all are the we can cover from your next lecture. But before we start from the next lecture, I will just give you some overview about thermodynamics revision. Okay, but it is on you that you have to revise all the concept of the thermodynamic whichever you have taught in your previous courses before we start this course, because this course is more understandable if you have the better knowledge about the thermodynamics one basic concept. Okay, so this is it. Okay, and because this lecture is just an introduction one, so we will not go for the full lecture for the 2 hours, but inshallah next time we will focus on our